Hello! This is going to be a quick crash course on heating and cooling curves. So these first four things are examples of what heating and cooling curves look like. Now when you take a gander at them, you can see they all have that same shape. They go up, over, up, over, up. Or if you're going backwards, they go down, over, down. But they still have the slants and the flat parts. They also tend to have, or they always will have, temperature on your y-axis. And your x-axis could be one of two things. Time, and this will be time as you add heat or take out heat, versus another way to do it would be energy. So in heating and cooling curves, what you're doing is you're taking the same substance. Like this is the heating and cooling curve for water. So it's water as a solid, a liquid, a gas, and any kind of mix of solid and liquids. Or if you look at another one up here, this is substance B, a kinetic substance, like maybe it's aluminum. It's aluminum as a solid, liquid, a gas, and so on. And so what we're going to talk about is what the molecular level view is, and what they're doing throughout each stage, and then the math behind it all. Okay, so I'm going to make you a little cheat sheet, note sheet here. So let's take the general curve here. We're going to be looking at temp, pretty much always degrees Celsius. You could go Kelvin, but pretty much Celsius. And then on the x-axis, you're going to be looking at energy input, is what we're going to look at, because it's going to be getting hotter as we go. Or you could also kind of look at time, like the amount of time as you added a heat. So the curves kind of go like this. So we're going to break down what's happening at each molecular level and then look at the math. Okay, first thing to note is what state of matter is at each part. When it's really cold at the beginning of time, this is all solid. And then this slant part is when it turns into a liquid, and this is a gas. So what's happening here at this flat part, this corner here is all solid, and this corner is all liquid, but in between those two corners, it's a solid-liquid kind of mix. Same thing going up here. This corner is all liquid, this corner is all gas, but in between the two, it's a liquid-gas sort of mix. So, that's the state of matter on each of them. So if we look at the names of things, like if we start at the top, when you are a liquid and you're going into a gas, what's happening then is you are boiling. Well, you could call it boiling, but what we really kind of call it here is vaporize, or vaporization. And when you're going, let's going this way, and you're going from a gas to a liquid, then you're condensation, or condensing. When you're going from a liquid to a solid, that would be called, solidification. You normally call it freezing, but the science word for it would be solidification. And when you go from solid to a liquid, you normally think melting. Well, the science word for that is fusion. Okay, so now we want to talk about real quick is what's happening at each of those kind of parts, like to the molecules themselves. We know that solids are really stuck together, really close to each other, and they have a high intermolecular force. We know that gases are really spread out. They have no intermolecular forces. So no IMFs. Strong IMFs. Intermolecular force is what holds them all together. And we know a liquid is kind of like a middle IMF. I'm not going to write middle IMF, but you can see that idea. So when we look at the slanty parts are actually changing in temperature. Like look at the solid to where it is a solid at its highest temperature. It's changed temperature. If you change temperature, it's going to change your speed. So I'm writing change speed. Each of the flat parts, when you add energy, you are using the energy to change the speed of the molecule. In other words, you're changing the kinetic energy of the molecules. That's what the energy is doing. But when you're actually at the flat parts, you're not actually changing the kinetic energy, because look at this flat part here. As you go across, the temperature of it doesn't change. The temperature is the same the entire time, which means the kinetic energy is not changing. Right? No change in kinetic energy. At this flat part, there is no change in kinetic energy. So what it's actually doing is it's changing potential energy. And what it's actually doing is going to take your strong IMFs, which is right here, the solid, and it's going to loosen the IMFs. So the change in potential energy here is you're going to loosen those intermolecular attractions. That allows for the liquid to kind of flow past each other. At the top here, we're changing potential energy to completely break the intermolecular forces. Because as a gas, they're not having any intermolecular force whatsoever. They're not attracted to each other at all. So that brings us to the length of these lines. I purposely made this line really long and this line sort of short. It takes a lot of energy to completely break intermolecular forces. If you're going from a liquid where they're kind of attached to each other to a gas where they're not attached to each other at all, you better give them a lot of energy to break that attraction that they have, any intermolecular force they have. But down here, the solid liquid, yeah, you need to put in some energy to make that solid kind of loosen its intermolecular force to create a liquid, but not as much as if you had to break them. So the distance, the length of these lines are this length for a reason. This brings us to another topic. Oh, I'll go blue. This right here is the temperature in which liquid goes into a gas, or that's your boiling point. This temperature right here, whoop, is when it goes from a solid to a liquid, or a liquid to a solid. Solid to a liquid is when you have the melting point, which is going to be the same temperature as your freezing point. So like a freezing point of water is 0 degrees Celsius. The melting point of water is 0 degrees Celsius. If you melt or you freeze, the process of melting and freezing is still a solid-liquid kind of mix, and that happens at 0 degrees Celsius. Boiling, you have a liquid-gas kind of mix, and that happens at 100 degrees Celsius for water. Okay, so let's go back and look at these graphs here. So here's water. Its boiling point is 100 degrees, and its melting point is 0 degrees. Let's take a look at a different graph. This graph has a boiling point of 90 degrees. This graph has a boiling point, look at this top one here, of 2,700-ish degrees. 2,700-ish degrees to boil it. That must mean they have really strong intermolecular attractions that you had to heat it up so drastically much for it to leave its friends. Between this substance A, this top chart, and this one right here, the stronger the intermolecular force will be this one, because it has such a high temperature in order for it to boil, such a high temperature in order for it to melt. It must be really attracted to each other. Something like an ionic compound or something like that. So the boiling point right here, the stronger the IMFs, the higher the boiling point will be. It's not always about the distance of the length. The length can be controlled by the actual mass of the object, like if you had 20,000 kilograms of something versus 5 kilograms, the length of the line will be different. But what will never change, no matter if you have 5 grams of something or 5,000 grams of something, is the boiling point. The stronger the IMFs, the higher the boiling point, no matter how much of the substance you have. So that's how I can tell from the chart that this substance A here must be something like an ionic compound to have such a high boiling point. And this substance B must have something like close to water, some sort of polar molecule in order to have a mediocre boiling point. Okay, so that's all the information with that part of what the molecules are doing. Now I'm going to hit up the math part of it. So if you want to do some practice questions, these first page as well as the second page is what are the molecules doing? How is it kind of working? That would be a recap of what I just covered. The next part I'm covering is actually some math part. That would be this page and then the next page. So looking at the math right here, there are some numbers in this chart that I'm going to kind of label here. If you wanted to figure out, assuming this is energy, if you want to figure out how much energy, the Q value here, how much heat do you have to input in order to get something from a liquid at its melting point to a liquid at its boiling point, you can calculate Q. And Q, in this case, you're going to use the equation of Q equals mc delta T. Things we've already used before. Q equals mc delta T happens at all the slant parts. Q equals mc delta T. Happens at all the slant parts. So if you took water and you heated it up and it was still water, then you're looking at mc delta T to calculate that, what we've already done before. The only thing that's tricky is taking a look at this chart, take a look at water. Here's your specific heats. Water has a different specific heat when it's a solid versus a liquid versus a gas. So it is different. So when you use Q equals mc delta T, you have to pick the correct C. Are you in the solid part, the liquid part, or the gas part? Then, going back to specific heat as a little recap also, taking a look at something that has a high specific heat, that means it doesn't heat up very easily. Specific heat is the amount of heat needed to raise 1 gram of substance 1 degree Celsius. So if you have a really high number, it's going to take a lot of energy to heat at 1 degree Celsius. It takes 4 joules to raise at 1 degree Celsius. While as a gas, it only takes 1.8 joules to raise at 1 degree Celsius. So it's a lot easier in the water state to heat up the gas than it is the liquid. So, going back to my picture here, the steeper the slope, the easier it is to heat up, or the easier it is to increase the temp, which means it must have a low specific heat. That's something we covered first semester, but it's a nice little recap. So taking a look at my slants here, my slants kind of look like the same slope, but if you look back at the graphs, they really don't have the same slopes. Like that looks like it's the same slope, but if you actually investigate the actual numbers, they're not. Here, the slopes are different. That one is just kind of drastically doesn't show enough. Here, if you look at the exact slopes, they're going to be different too. The specific heat is different depending on the substance and its state of matter, and it's controlled by, the slope is controlled by specific heat. Okay, the other numbers that we have here is the heat of fusion and the heat of vaporization. Those numbers, are found in here. So that's when we want to find the heat of like a flat part, right here. That kind of Q, you're going to want to use the equation N times delta H. Now delta H could be whatever you're looking at, like in this case, condensation. Delta H of COND, condensation. Or you have a delta H of vaporization, VIP. You have a delta H of fusion, and you have a delta H of solidification. And what this all means is, change in H is defined as the molar heat of blah. So the molar heat of vaporization is the molar heat, or the amount of heat needed to vaporize 1 mole. So I'm going to put fill in the blank here as an example. Molar heat of vaporization, we'll call it. That's going to be defined as the amount of heat needed to vaporize 1 mole of that substance. But if you change the blue into something else, like you wanted to say the molar heat of fusion, it would be the amount of heat needed to fuse 1 mole of that substance. So, if we know that 1 mole of the substance, like in this case here, 1 mole of water will take 6.02 kilojoules to fuse. If I happen to have 2 moles, then it would take about 12. If I have 3 moles, it would take about 18. So to figure out how much heat it takes to actually vaporize something, or condense it, or whatever you got, you just have to take the number of moles, N, and multiply it by the heat of whatever it is you're looking at. Change in H, change in condensation, solidification, whatever you got. So that's also the equation for this flat part. Q equals N delta H. So those are the 2 equations. Slanty parts, you use the C. Slanty parts, you use the C. Flat parts, you use the N delta H. Once again, these problems in here, this goes through the slanted part, and this goes through the flat parts. And then this last page is where you're going to kind of put them all together. So, I'm running out of time in my clock here, but let's give an example here. If you wanted to find, if you happen to have water, melting point is 0 degrees Celsius, and 100 degrees Celsius is boiling point, and you said, I've got water at 72 degrees. Boom, right here. You have water at 72 degrees. And I want to know how much heat is it going to take to raise it to 150 degrees. Here's 150 degrees on your chart. Kind of a little sloppy. So if you want to figure out how much heat that would take, you have to go up, you have to go over, and you have to go up again. So you've got to do 3 equations and add them up. Here's the slanty part. You're going to do Q equals MC delta T there. Here's the flat part. You're going to do Q equals N delta H. Here's the slanty part. You're going to do Q equals MC delta T. And then you're going to add up your numbers for all of these. And that would give you the total heat you need to go from your starting point here to your ending point here. Now I will say I haven't seen in any AP tests a real long problem like this. I don't think that they're going to do that sort of thing. I will tell you that I just saw an AP problem that'll go from here to here, but it's really kind of a simple math because you're looking at a 1 mole of the substance. So I wouldn't concern yourself with, oh my gosh, what if I have to go from here all the way to here? I don't think that kind of problem is going to be on there. I think it's more conceptual, like what's really going on in heating and cooling curves that you want to look at. But if you're looking for practice problems, these are a great way to go. I think I have 30 seconds left of my thing. I'm going to show you an AP question that was on a test before 2013, but it has to do with supercooling a substance. This little dip in here is supercooled substance. And so if you look at the answer, I'm going to end my video this way so you can pause it and take a look at it, because it's going to run out of time here. Here's the answer. All right, good luck.